it. So, but I will make that go away so that nobody gets a headache from that screen. All right. So, recording officially started. Thank you for being here. Thank you for your flexibility. Welcome to quarantine. I'm feeling fine, but I'm still COVID positive, so I'm hiding in my basement. This morning, I went through and looked at the two things that you had due. One was your first formative assessment, and everyone should have their 2 points. I updated grades accordingly, so when you log into the homework portal, you can see all of your points. I looked through your answers and provided some brief comments, and we'll go over those in just a second as a class. And the other thing that was available is homework 0. So here we are. Homework 0 for up to 2 points extra credit. That one I'm not taking off any late points, so I sent out a reminder to a few of you who hadn't had a chance to do it yet. Go ahead and do it when you can, please. And I just want to make sure that everybody can access the system. And don't forget to hit submit and then re-enter your number. That always happens at least once in an assignment, and I'm hoping to cut down on that. So after you hit submit, you have to re-enter your ID number just to make sure that you actually meant to submit. That way no one submits by accident. So those two things are there. In terms of materials for today, we're still going through Lecture 2 and Example 2, and I wanted to make sure you were aware of. So Lecture 2 slides are here on the webpage. Example 2 has a compiled PDF that I'll be going over that has annotated syntax and output, but all of the original files that built Example 2 in terms of the dataset, syntax, and output are available in this zip folder right here. So when it comes time to start on homework 1, which is not yet available, but I'll let you know when it is, go here, download the original source files. Don't try to copy out text from the PDF because I found that that doesn't always work well. Sometimes there's extra characters that screw things up. So the original source files is what I would recommend starting from when you're going to do your assignment. Okay, so I have in front of me the first formative assessment. We can go over together as a group. All right, everything good so far, folks? Good, all right. If my video cuts out or my audio cuts out or I lag or I freeze, please let me know. I've accidentally shut off my video sometimes with hand gestures. I still don't know how I managed to do that, but I have. So I think I've shut off everything that would make that happen, but I could very well be wrong. So please let me know if there's any issues as we go forward. So first question here on formative assessment number 1, if patients from a single clinic who all see the same physician, and you're measuring outcomes from patients assigned to 2 different groups, we'll call it treatment and control, how many levels of a model is this? So this is a chat window question or a finger question. You can hold up a number of levels if you wish, or you can talk. Your call. Yes, consensus so far 1. 1 is correct. Now, several folks wrote down something other than 1. So for those of you who are saying 1, tell me why. Why is it only a single level of a model needed to predict an outcome?
Is it because there's only one source of variation?
Yes, that's the idea. So we have 2 groups, treatment versus control. Group does not need to be a level because once you put in a dummy variable, binary predictor for which group someone's in, that addresses any dependency of the fact that people from the same group would have a similar outcome. So from there, we're assuming people within the control group are independent and people within the treatment group are independent. If that's not true, then we'll be wrong to some extent. But based on the wording of the question, that would be independent observations after just controlling for group as a fixed effect, which makes it a single level model. So any questions on that? Good. Okay. The next question apparently has 2 different correct answers, as I saw that several of you interpreted the question one way and others interpreted it a different way. So if the previous study were extended to 50 different hospitals, where 25 of the hospitals were treated as control sites and the other 25 were treated as treatment, now how many levels do we need? Got votes for 2. I would also accept 3. Yes, so it depends on doctors in the middle. So if there's still a mapping of everyone in the same hospital sees the same doctor, then doctors and hospitals are one level sort of put together, confounded. If patients from the same hospital see different doctors, though, if there are multiple doctors working within the same hospital, then that would create a 3-level structure of patients nested in doctors nested in hospitals. If it's all one doctor within a hospital, then it's just patients and hospitals as 2 levels. That does assume, though, that everything is nested. Is it possible that doctors might work at different hospitals? Sure. So if that is the case, then it's still 2 levels potentially, but hospitals and doctors are crossed. So then that would be 3 dimensions of sampling, but patients would be level 1. Patients would be not nested in doctors as 1. So nesting versus crossing dictates what the model setup would look like, but still conceptually, if there's different doctors in the mix, that's 3 different types of sampling. It's 3 different sources of variability, and each one would need some kind of error term representing variance left over. So that's when we're in the multi-level land. All right, questions on that?
Lisa?
Yes, that's me.
Oh, sorry.
There
Yeah,
you are.
that's sorry, but can you repeat your last answer because I couldn't hear you well some seconds, please.
Okay, yes, sorry about
Thank
that.
you.
So what I had intended this to be was just 2 levels of patients within hospitals, assuming that it's a mapping of 1 doctor per hospital. But lots of folks interpreted it differently, thinking that there were still multiple doctors and multiple hospitals. So there's 3 dimensions of sampling if there's multiple patients, multiple doctors, and multiple hospitals. The distinction then is whether that becomes a 3-level model or a 2-level model that's crossed at level 2. It would be a 3-level model if each doctor only worked in one hospital. Then we would have a strict nesting that's hierarchical of patients at level 1, nested in doctors at level 2, nested in hospitals at level 3. If doctors work at different hospitals, then it's still 3 dimensions of sampling, but it's a 2-level crossed model instead, where patients are nested in doctors, patients are also nested in hospitals, but doctors and hospitals are both crossed at level 2. So that's known as cross classification or a crossed model, in short. Does that help? Yeah,
Yes, Lisa, thank you.
sure. My pleasure. And questions coming in from the chat. Let's get those. If it's crossed at the doctor level, would that assume that the doctors are exchangeable? Yes, I think, if I understand the question.
Yeah, so kind of like I'm thinking of this in like an item, like a test framework that items are exchangeable if like over time, if somebody takes a test multiple times, then the items are assumed to be exchangeable with each other. So would the doctors be assumed to be exchangeable in that? If there's like a level above them,
Okay,
if that makes
yes.
sense.
Yes, yeah, I'm with
Okay.
you. So if it's the 3-level situation where patients at level 1 are nested in doctors at level 2 are nested in hospitals at level 3, then putting in, for instance, a random intercept at level 3 for hospital variation would presuppose that all doctors are equally related to each other from the same hospital. They're exchangeable.
Thank you.
Yes, and in this context, that's a reasonable assumption. It doesn't work as well in a longitudinal setting to assume that occasions are interchangeable because there's usually some sort of systematic change that's happening, and you'd want to pay attention to which occasion is which. But in these types of clustered designs, doctors would be assumed interchangeable after you condition on any similarity due to which hospital they work in, or hospitals, as it were. Next question. What if patients saw multiple doctors within hospitals, 2-level crossed at the first level? Oh boy. Yeah, it would be. It's three dimensions, but they'd all be crossed together. And I know it's starting to hurt, right? For cross designs, by the way, the two-level notation that we introduced last time starts to fall apart really quick, and just writing a composite equation gets a little bit easier. If you have enough observations, you can potentially estimate not only random main effects, sort of like which patient is which hospital is which doctor is which, but also potentially interactions. So if you have a patient who sees like the same doctor more than once, then you can potentially pull out a patient by doctor interaction as a random effect. That's sort of heading down a rabbit hole that I didn't really intend, but yes, these things can take on a lot of different forms, and trying to figure out what's nested and what's crossed is an important precursor to figuring out what the model would look like. Does it mean that if doctors are working at both hospitals, then there is two levels? If a doctor works at more than one hospital, then doctors are not nested in hospitals, they are just crossed. And then the question would be, are they crossed with patients also? If a patient sees more than one doctor, then the answer is yes. And now you see why this course could be not only an entire semester, but probably 2 semesters if I wanted it to. I can take longitudinal and stretch it into 3 easily. I'm sure I could do the same with cluster. Is it cool if I'm lost? Yes. Yes. The answer is yes. Absolutely. I'm just trying to go for the basics here, where the idea is, do you have one dimension of sampling or do you have more than one? More than one means some kind of multi-level model is needed. In the first example, where we just have people and people are assigned to 2 different groups, it's not more than one dimension after you control for which group they're in as a fixed effect. Not everything has to have random variance beyond the fixed effect. That's the take-home point. Does that make it better? Yeah, I feel like if I go down the rabbit hole, then I owe you, like, to backtrack back out of it and then come back up to the surface. But life is complicated, right? Like once you start looking into this stuff, like I'm not, these are all realistic examples of how people can be grouped and how those groupings can change over time, or they can become contextual. Even in the situation where you think of the classic, like students from the same school, students change schools over time. That creates a crossing instead of a nesting that can be fairly tricky to handle. So this is life. This is how it goes. Okay, any other questions on that topic? Thank you for your honesty. Maybe an easier one? So the common underlying feature of general linear models, as an example, standard linear regression or analysis of variance, or ANOVA for short, and generalized models, where ized means the use of some kind of other distribution and likely a link function to keep predicted outcomes within some kind of boundary. If none of those words make sense to you, that's okay. I'm just saying this is for normal outcomes and not normal outcomes. What do they have in common that makes them insufficient for multi-level data?
Constant variance.
Constant variance. I'm gonna say that is part of general, but not usually generalized. So that would not be it yet. 2 guesses in the chat window. Independent residuals. Yes, indeed. Yep. Independence is the thing. So general linear models, generalized linear models, what they have in common is the idea that residuals are supposed to be independent. Beyond that, general models assume normally distributed residuals, which implies constant variance, and generalized models don't have to. If you pick a different distribution, that usually implies some kind of non-constant variance function. But what they do have in common is it's built for 1 dimensions of sampling. That's the key idea. If you only have 1 dimension of sampling, then those are where you go, and what type of model depends on what type of outcome you have. If you have more than 1 dimension of sampling, which is the whole point of this class, then we can extend both of those families of models to have multiple dimensions of sampling, which means multiple kinds of residuals. And that's what we started talking about last time.
So if you said for the residuals that there was only one pile of variance, is that acceptable or that's not the point? The point is that they're individual.
I would accept one pile of variance as a correct answer. So one pile of variance to me is the same thing as saying there's only one dimension of sampling that units vary across, and that is the same thing as saying that they are assumed independent. One dimension.
Okay, thank
To
you.
me, yes, other people may disagree with those connections, but I think those are sufficiently synonymous for present purposes. Can I explain question 3 again? Yes, that's where we still are. So general models are for outcomes that are conditionally normal. Generalized models are for outcomes that are not normal, so binary counts, other skewed otherwise. What they have in common is that both of them are built for single dimensions of sampling, where the units that are being sampled over are assumed to be independent after you condition on all the model predictors. Said differently, independent residuals. Conditionally independent is referring to the residual part, not the original outcome part.
Thank you.
Go. Other questions or clarifications? Happy to repeat or clarify as needed. No? We're good? All right, then question 4. Thank you, everyone, for playing along to question 4. I put up an announcement inside Icon. I have built a YouTube playlist of everyone's choices. It is unlisted, which means you need the link to get to it, but once you have the link, you can play it. For mine this year, I picked a newer theme song, meaning I haven't chosen it before, but it's definitely not a new song. I've been listening a lot to my Bangles Greatest Hits CD in my car, and I picked their cover of Hazy Shade of Winter because the opening guitar solo, right? Like that's the walkout music, like bam, 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 bam. I know, a CD. I drive a 2008 Corolla. It has a CD player and a radio, and that is how I roll. I have a CD case filled with CDs, and several of them are like mixtape CDs that I made myself. That is how I roll, and you will pry my CDs out of my cold, dead hands. I am hoping someday to give my car to my son to drive. It only has about 75,000 miles on it, which is why I'm still driving it. So I did not rip them from LimeWire. I used, whatever Windows Media Player or whatever you can use to make CDs back in the day. Question, Jacinta.
Well, first, I just wanted to say I have all of my CDs as well, so and mixed ones. And second, I just the song that I picked, "This Girl Is on Fire," is mostly because my 4-year-old Elijah is that's his favorite song right now, and he screams it at the top of his lung. This girl is on fire, and it's just really, really like motivating. So I just wanted to share that.
I'm grateful that Hugh hasn't discovered that one yet. He was obsessed with, he calls it Shrek. The rest of you would know it as All Star. Obsessed with that song for a very long time. The Kids Bop version, apparently they wore out at his school when he would ask for it. So, but I'm looking forward to seeing your selections. I didn't have a chance to listen to all of it, but I listened to enough to know that we have many creative choices. So thank you for playing along. I'm one of those people that has nothing but old music pretty much in my repertoire, so learning some new things is a good deal, especially for upbeat workout kinds of music. All right, so that's all I had to say about that. Any other quiz questions before we shut the window? Good to go. All right, bye-bye. All right, then we are back in lecture 2. Let me make sure that the recorder is still going. Yep, looks good. Normally there's like an error message down here if it's like encoder overloaded. And I was watching for that. It appears to be happy, so yay for us. All right, so tell me what you remember from last time. Last time was Thursday. It was a while ago. But I will take words, gestures, letters. Anything you got? We got the title slide here to jog your memory. Have more than 10 schools. Oh, that's a good one. Yes. If you're going to have a school level intervention, then the number of schools dictates your power to detect the effect of the intervention. And 10? Probably not enough. Is new. Yes. We got a new letter in the mix. So I typically use E as the residual in a regression type model, and we added to E with U, which is going to be level 1 or level 2. I'll give you a hint, it rhymes. Indeed. And yes, if you weren't here and you're catching up, that's just fine. That's why we got the YouTube recordings. You can catch up as much as you need. So yeah, we got a new letter. The idea is that differences between clusters at level 2 are represented by the variance of the U's, and differences within clusters at level 1 are represented by the variance of the E's. So we take what used to be sort of one pile of variance and we split it into two. Level 2 random intercept, which is the U, and level 1 residual, which is the E. It's better to have one student per school in 100 schools than to have 50 students in 10 schools for the ICC. For the design effect, yes, that is true. In terms of reducing the design effect, which is the penalty that you have when you have clustering in your data, reducing that would involve either having a smaller ICC or having a smaller cluster size. So fewer people per cluster reduces your design effect. At the same time, fewer people per cluster reduces your ability to examine cluster specific patterns and to be able to examine the extent to which they differ across clusters. If they're not reliably measured per cluster, it's tough to find the variability across clusters in that. So you have competing goals in designing studies. What may be best from one point of view may be less useful from a different point of view. Let's see, what else? I think we hit all the big stuff. Do you want to look at maybe some notation in ICC again for review? Would that be useful? Kind of wade back in here. All right, let me get to, let's do this slide real quick. So this is my schematic of the idea of taking all of the variability in an outcome and dividing it into two piles, or two variance components, by the way. If I'm writing a paper, it's a variance component. If I'm writing my book, it's a pile, because you can write whatever you want in a book. That's the secret. It's not actually reviewed. So we have what's known as an empty means model, meaning I have only a fixed intercept here that start as the starting point for each person's outcome. I add to it our new friend U. U0 is the random intercept that varies across C for cluster. So subscripts in these models are very important because they tell you whether something is fixed or varying, and if it's varying, what it varies over. So the fact that this only has a C means that each cluster gets one of them, and it varies only over clusters, as opposed to our friend E at the end here, which has a PC, because each person gets a residual and each person is nested within a cluster. So it gets both. Any variable that is a level 1 variable will have PC. So that's why Y has a PC, E has a PC, U is actually level 2 in this combined equation. So we have why is it that some clusters have different means than others, and U is the deviation of each cluster's mean relative to the mean of the cluster means, which is my fixed intercept here. And then E is the difference between each person's outcome relative to their cluster's mean. So it's like a peer-to-peer comparison at the E level. U is a cluster-to-cluster comparison at level 2 instead. Here is multi-level notation then for the first time. How you write equations to describe your models is up to you. In some fields, it's almost exclusively in this kind of hierarchical placeholder notation setting. Once the model gets really complicated, this is helpful because it can help keep things organized. But in other disciplines, you would not see this, and you would only see like a composite equation down here where there's no placeholders. So what do I mean by placeholders? So in level 1 here, beta 0c, I call that a placeholder because what it does is hold actual parameters. Beta 0c is not a parameter. It's not a single estimated quantity. It is a container for other estimated quantities. At level 2, beta 0 is how each cluster is going to get its own mean. We start with the fixed intercept, gamma 0, 0, which is the mean of the cluster means. And then U0C is how far off your cluster's mean is from the fixed. So if you're from a cluster that does well, then your U is positive. If you're from a cluster that does less well, your U is negative. And then putting those together is how each cluster gets its own mean. Beta 0C then comes back here and we pick up E as the difference between what each person has for their outcome and the cluster mean. So all in all, there's 3 parameters. We estimate the fixed intercept. We estimate the variance across clusters in the random intercept, and that's level 2 random intercept variance. That's the tau squared thingy here. And we estimate a variance across people, where we assume that each cluster has the same amount of people variance. That's an assumption, but that's a common place to start. So we have 2 kinds of variance, 1 fixed intercept, 3 parameters in total, regardless of how many people you have, regardless of how many clusters you have. Okay, with me so far? So then the next logical question is, well, I've got 2 piles of variance, like which one's relatively bigger? To answer that question, we have our friend Interclass Correlation, where the numerator is the amount of level 2 random intercept variance that represents between cluster mean differences, divided by that plus the remaining level 1 within cluster residual variance. So this ratio you can think of as telling you 2 things, different explanations but are equivalent. One is that it's just straight the proportion of variance that's due to cluster mean differences. The other is that it tells you the average correlation of people from the same cluster. You can think of it either way. So ICC ranges between 0 and 1, where 0 would mean no clustering whatsoever, no cluster mean differences, and 1 would mean all cluster mean differences, no within cluster variation, people are identical to each other. Very infrequent that you would see something like that, but still theoretically possible. Another way you can think about ICC is that it's an effect size for the amount of dependency you have due to constant cluster mean differences. It does not mean that we've explained any variance. It just means that we've figured out how much of the total variation is because some clusters have a higher mean than others, that's level 2 random intercept, and because some people within their cluster do better than other people, that's level 1 residual. Got some pictures for small versus large. Then we had some numbers to throw on here. So an example from a data set that I borrowed from the Snyders and Bosker textbook, where we're predicting language outcomes, fitting an empty means model and adding a random intercept, yielded, if I put the numbers that are in my output here into an interclass correlation, it's 0.22, meaning that's the expected correlation of students who go to the same school. It's also the proportion of variance that's due to cluster mean differences in this outcome. I think, yeah, we got through design effect as the next thing. So design effect is something that is often used in study planning when you have a clustered sample and you're trying to figure out how many more people you need because people are clustered. So a design effect is a penalty function. And 2 things go into it, ICC and level 1 sample size. So unless ICC is exactly 0, you will have a design effect that is greater than 1 to at least some extent, where 1 is the smallest it can be, meaning there is no penalty. So design effect is the denominator of this equation here that is used to compute effective n. So the number of actual observations you have divided by the design effect tells you how many effective in terms of the amount of information your people tell us. So we had a couple examples of that where design effects of around 2 could occur because you have a relatively large intraclass correlation but a small level 1 cluster size, or you could have a small interclass correlation but a large cluster size. So both of these things are important. In the example data set, the design effect worked out to be about 5 because we have both a relatively large cluster size and a relatively large ICC. So if I were going to plan this study from scratch, I would need to have 5 times as many students as I would if the students were actually independent and not from the same clustering. Question, Jacinta.
Yeah, so this is the why that one study with 10 schools, this is why it wasn't that effective, right? This design effect right here. You use this
That's a
or
separate issue, actually. So the example that I shared last time where we had 10 schools and 5 schools were assigned to be control schools and 5 were assigned to be treatment, the issue there was that they thought they had plenty of power because they had like 30,000 students across these 10 schools. But at the school level is where the manipulation happened for treatment versus control. So in terms of any one school, all of those kids are either control kids or they're treatment kids, meaning that within schools, the manipulation was a constant. So it's not at all relevant how many students you have per school if the predictor that you care about is at level 2, which would be the case if the whole school were assigned to control versus treatment.
so you found that out by looking at power, not by design effects.
You could look at if you look at power, you would have power given by 5 schools in each condition, and so you'd have to figure out like what your minimum detectable effect size would be at that level, which is basically positive infinity. You could show this via simulation, so this is something you could do easily to demonstrate to yourself, like make up a data set and keep adding kids to it, and you'll see that power does not change as a function of level 1 sample size if what you care about is level 2, because the reliability of the mean you're estimating per cluster gets really strong real quick, and adding more is not going to have a visible payoff after you have like 10 kids or something like that per school.
Okay, so it was more logic that you used than
Yes,
anything else, not a
logic and math.
specific equation.
Yes,
Okay, okay.
yes, it's
There wasn't a
demonstrable.
specific equation that you used to show that,
Nope, that was just a
or was
story.
it? Okay,
Yep,
okay,
just
thank you.
yep, yeah. No, I'm happy to clarify. Let's see questions then. If the predictor you care about is level 1, is that where you focus on sample size? Yes. So that's where this would be relevant. So if the people came to me and said, well, I've got 30,000 kids and I want to look at kid whatever predicting some kid outcome, 30,000 sounds like a lot. But then the question would be, how strong is the clustering effect? And that is a function of how much variance is actually due to cluster mean differences that has nothing to do with the kids, and how many kids are there per cluster. So in terms of like best case, worst case scenario, let's use these numbers here on this page. We have 35, 66 students. So if I had a design effect of 1, because the design effect formula starts at 1, that's the lowest it can go, then the only way that it will stay at 1 is if ICC is exactly 0 and this part drops out. So if I have 3566 and a design effect of 1, then my effective sample size is the same thing as my actual sample size. Worst case scenario would be what? In terms of effective sample size.
The design effect outweighs the denominator gets too big.
Denominator gets
That'd be
too
right.
big. And I don't even have to do the math. I can tell you that like the maximum, like the worst case scenario would be an effective sample size of 191. That could happen if you only had 1 student per school, or if every student who went to the same school was exactly the same in their outcome. Then your power for student things is actually the number of schools. So somewhere between 3566 as best case scenario and 191 as worst case is what you actually have in terms of the number of students. So when you're trying to plan a study, you would like to try and make reasonable guesses as to what the ICC would be and to what the expected sample size per cluster would be, so that you can overcome that design effect by adding more people. Next question. It really is grain size. If you're comparing schools, the number of students isn't important. Is that right? That is right if you're talking about the intercept, so mean differences. If you're talking about comparing schools in a slope, that's a little bit more complicated. So if you're looking at, say, the relationship between, let's go with the amount of reading that a student does at home and then their subsequent performance on some kind of reading test, something like that. If you want to look at whether that relationship between reading at home and doing well on the test varies across schools, you need to have a decent estimate of that relationship within each school first as sort of a logical condition. Like you need to reliably estimate each school's slope, and that depends how many students you have within that school. So from that perspective, you want to have both a good enough number of students per school to get a good enough slope within each school and enough schools to be able to estimate the variance of that slope across schools. So that's like 4 weeks from now. But if you're just talking about mean differences, then yes, what you said is correct. The number of schools is what matters. And any school predictors, your power to detect the effect of those based on number of schools. Bayes doesn't have to worry about design effects. Oh, yes, they do. Bayes does not fix clustering.
You just give a prior.
No, 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 no. The rules do not change because you've added a prior distribution to your parameters. No. But yes, some of these ideas of design effect in ICC show up in evaluating convergence in Bayes because you run multiple chains and you want to have basically no interclass correlation for differences across chains relative to differences within chains. So these same ideas do show up in that context. But no, Bayes does not fix clustering.
So on the flip side, a design effect of one.
That's best case.
That's the best. Okay.
Yep.
Okay.
Because then that just means sample size divided by 1. So this is the point where I said I had a soapbox, remember? It's time for the soapbox. So at this point, usually people would ask me, well, I read from some place that was published that if I have an ICC of less than 0.05, I can just ignore it. Well, look at this formula. An ICC of 0.05 may translate into a small design effect if you don't have that many people per clusters, or it could be ginormous. So there is no cutoff for where enough, like that you don't have enough clustering to worry about, only 0. But even then, you still have to care. So here's the rationale, and I'll show you the math on the next slide, but basically conceptually, the way that these piles of variance are created by the model, they are inherently tied together. And any time that you reduce the variability of the e's across people, that will necessarily translate into additional variability at level 2. So what can happen is that you can start off with an empty model that has an interclass correlation of 0. It thinks there is no level 2 random intercept variance. It thinks there are no cluster mean differences. ICC of 0 is what that would mean. And you might be like, cool, I get to go back to regression. No. Because once you put in people predictors at level 1, that will reduce the level 1 residual variance of the e's, and that will in turn introduce additional variance at level 2. So your conditional interclass correlation, meaning after factoring in your predictors, will become greater than 0 if you've explained any people variance at level 1. That means it'll come back. And so the interclass correlation you end up with when your model's all done being built, the amount of dependency that is left over after controlling for your model predictors depends on 2 things. How much was there to start with, and how much of the level 1 variance you were successful in explaining. The better your model at level 1, the more your dependency is going to go back up at level 2. So that's one reason. The other is that any person predictor that you put in your model is almost always going to be not just a person thing, but a cluster thing. Because for the same reason that we need a multi-level model for people on the outcome side, we need to address the fact that predictors also have this type of dependency to them. And any predictor is going to be partially a person thing and partially a cluster thing. And fitting a single level analysis ignores that problem. That's coming, if slopes were like 4 weeks from now, that's probably going to be another 6 weeks from now or so. We'll get there. But this is sort of giving you my introduction to the motivation for why other strategies based on just adding corrected standard errors or ignoring it are not going to be adequate most of the time. So what is this tying together? I'll give you some math here. Any true model estimated random intercept variance is not just the means across clusters. Like if you took your data set and you asked for a mean for all people from the same cluster and you outputted that to a different data set. So all packages know how to do this. You can take a mean across rows, put it in a new data set. And if you took the variance of that column of cluster means, that variance is going to be larger than the variance that shows up on your model output. The reason for that is that built into the estimation is this penalty function that says, well, some of it is true cluster mean differences, but some of it is just noise. So like if I took all of you in this class and I randomly assigned you into multiple groups and I asked each group to compute their group's mean height, would all the groups have the exact same mean height? Not exactly, right? It shouldn't be very different if random assignment actually works, but there's a little bit of wiggle. So the model estimation tries to anticipate how much of what we think is cluster mean differences is actually just due to chance and how the people were thrown together. And it operationalizes that idea of wiggle as level 1 residual variance divided by the level 1 sample size per cluster. So it's like what you actually should have plus noise is what you get in your cluster mean data set. So then we work backward. It's like, well, I'm just going to say then what I get in the output is cluster mean minus noise. Fine. So then here's some numbers to show what might happen. So let's say that we get an observed variance across cluster means of 4.65. We have level 1 within cluster variance of 7, and I have 4 people per cluster. Well, that works out to be a level 2 random intercept variance of 2.88 after correcting for the noise factor. Fine. Well, let's say that we then add a super good predictor at level 1 and it reduces the level 1 within cluster person-to-person variance from 7 down to 2. Well, now, if I stick that in the same formula, the penalty function, the amount of noise that's expected based on just random fluctuation, is smaller. So it looks like we have more cluster dependency, more cluster mean differences after the predictor than we did before. So because of this tie together, your level 2 random intercept variance will go up when you explain only level 1. And therefore your interclass correlation will go up, and therefore your design effect will go up. So even if it starts at 0, it may not stay there if you have a good level 1 set of predictors. So that's my sales pitch. Yes, you need a multi-level model. The answer is always yes. So questions or comments about that idea? Cheers. Happy Garbage Day. Except to those of you with Garbage Day on Thursday. I'll wish you a happy Garbage Day then. No questions? No comments? No, we're good? You believe me? Just do the multi-level model is the answer. Okay. All right. So here is something else you might want to report. Those of you who've had longitudinal with me, I never talked about this in that class because no one ever cares in the context of longitudinal, but in clustered they sometimes care. There's something called ICC2, which is a variation on the theme. It is reliability of a cluster mean. So this may be a question in terms of sample size planning. How many students do I need per school to get a good estimate of the school's mean? Where good means like what proportion of its variance would be due to true differences as opposed to error. So the same idea of reliability that you may have found in measurement classes, the idea of true variance over error variance plus true is the total, shows up here. So in the same set of numbers here, we had ICC1, which was the proportion of variance at level 2 due to cluster mean differences was 0.22. ICC2 looks very, very similar, except for the error part is divided by level 1 sample size in this formula. So then that knocks down the contribution of the residual. The logic here is that it's like how much residual per person are you bringing, where you have more people that brings it down. So if I put the numbers in here, the reliability of the cluster mean given these values would be about 0.845. So I'm saying that that would be the reliability of the mean for each school. And by the way, for those of you who've taken measurement model classes or structural equation modeling, this is directly analogous to the Spearman-Brown formula for reliability that assumes that items are exchangeable. How many items do you need? More. How many people do you need? More. Same exact idea. Question. All the world is an MLM. Yes, it is. This IC2 is different than the ones when we're using 3-level modeling, same notation. That's because I didn't invent this. So ICC2 is what everybody calls it. ICC level 2 or ICC level 3 is what I had talked about when we're doing 3-level modeling, because once you have 3 levels, multiple types of ICCs are possible based on what you put in the numerator and what you put in the denominator. So it's very similar notation, but not exactly the same. And yes, I know that sucks, but I didn't make up that one. Question from Vladimir.
Yeah, Lisa, in that case, can we change the 19 per the mean of our level 1 sample size if we have an equal sample sizes across groups?
Yes, so there's different ways of computing this, and for instance, there's an R package that will spit out the reliability of every single separate level 2 unit based on the sample size of that particular unit, and then you could aggregate those in some way if you wanted to. You can also decide whether you want to weight each school sort of by the different sample size or not, and I found a couple packages that will do that as well. So I don't think people have universally agreed on like the right way to compute this, which means you would probably want to say more specifically how you got it, but just the general idea is that this can help you determine how many people you need per cluster to get a good estimate of your cluster, which takes into account how different people are from each other. So from the perspective of measurement, like I don't like the idea of thinking of this as error, because like people may legit differ from each other. It's not the same as like an error, like a bad item in a test, but how different people are from each other certainly is relevant in figuring out, you know, how reliable your cluster mean is. The more variance you have within a cluster, the harder it is to nail down a good estimate of the mean. Okay, 122. We're
Lisa,
hanging in
follow-up
there.
question.
Yes, go ahead.
Sorry, yeah. Is there any kind of threshold related to this value? For example, if we have a value below 0.0, is that good or bad?
Depends
Or
on where you're
acceptable,
trying to
maybe?
publish. That's what I would say. Rather than saying I have acceptable reliability or something like that, you could just say my reliability is 0.845. And you can let your readers put whatever verbal labels you want to on that. This is also useful for study sample planning types of things too. For those of you who do N of 1 type designs, I'm never going to remember the proper name for that, but Alex, I'm thinking of you and a few others that I've talked to. Like, how many observations do I need per kid? Same principle. Like, if you think of this as repeated measures for a single person, then the same formula would work, except people are level 2 and repeated observations over time would be level 1. Single case design. Yes, damn it. Why can't I ever get that right? N of 1 is like how I learned it, I think, first, and then no one else uses that phrase. Because you can have multiple people within a single case design. They would be fixed effects, though, because you wouldn't have enough power to estimate a good variance across very few people. Do we need to remember all of these formulas? What do you think, folks? Can I get a thumbs up for yes, I need you to memorize formulas, or a thumbs down for no? The answer is always no. No, you do not need to memorize any of this. You do not need to memorize anything, really. What you need to have is resources. So software will have the formulas built in. Textbooks will have the formulas. I need you to try to understand the concepts. Like what goes into the formula, right? Like if you think about the ingredients here, random intercept variance is an ingredient, level 1 residual variance is an ingredient, and level 1 sample size within a cluster is an ingredient. And it works that you have the more your random intercept, the higher the ICC, the higher your reliability. The more people you have, then the less of an impact the residual variance has, the higher your reliability. So just sort of a conceptual, like how do these things fit together is what all I need you to have with respect to the formulas. Now, however, I will say that in terms of memorizing things, vocabulary is essential. Like when I say level 2, immediately what should come into your head? Give me some words that go with level 2. We'll turn this into a review opportunity. What goes with level 2 in this class? What's one word that will always work no matter what class you're in? Whoop, there it is. Between. Yes, you can always say level 2 is between. Between what depends on the context.
Lisa, I cannot hear you well. Not yet.
Thank you for letting me know. Turns out that unplugging and plugging it back in still the best method to fix tech problems. I know. If that didn't work, I was going to start hitting things, so it's probably just as well. Normally, I take that as like a sign from the universe that it's time to be done. But if I get it back, then it's not quite time yet, but very close. What was I rambling about? Oh, reviewing. That's what I was doing. Yes. Level 2 between. Absolutely. The corollary to that, level 1, ... If level 2 is between, what's level 1? Within. That set of vocabulary always maps. So in this class, level 2 is between cluster. Level 1 is within cluster. Level 2 is random in terms of the variance name that goes with it. The U is a random effect. It's an intercept, more specifically. In a couple of weeks, we'll have intercepts and slopes. Level 1, E, is residual. I'm always going to stick with those terminology so that we do avoid confusion. So to recap, no memorizing formulas, no memorizing code. Vocabulary, though, I need you to hang on to because I'm going to add to it. And rattling off the top of my head, level 2 between blah, 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 like that will go a lot easier if you've already attached at least the first couple words to that. So one of the reasons that at the beginning, at least, I try to use all the words in every sentence is to help you keep tying them together. So level 2, random intercept, cluster mean differences between cluster. Okay, there. ICC2, that's where we were. And another thing that you can do out of an empty model to try and help convey how big the differences are. So those of you who are working with stakeholders in an educational setting, right? You might be learning these fancy multi-level models, but the school principal has no idea what the hell you're talking about. So you can say to this person, you have an interclass correlation of 0.3, that's huge. And they'll be like, is that good? I don't know. So how can you make this a little bit more interpretable is to take the amount of variance that you have across these cluster means and use that to put the cluster means back onto the scale of the outcome. So I'm talking about a type of confidence interval that you probably haven't seen yet because it's not your typical confidence interval. It is a random effect confidence interval rather than a fixed effect. What do I mean by that? Okay, so here's my numbers. So in this empty model example that I have, on average, across the schools, the average school mean is 41. And here's the standard error that gives the expected inconsistency of that school mean across repeated samples, hypothetically. Down here are my variance components. So 17 is the variance of the school means. Level 2 between school cluster mean differences is 17. Within school, level 1 peer-to-peer differences is 62. A typical confidence interval for the intercept is really all about the fixed intercept. So if I were going to build that, I'd start with 41 as the middle, plus or minus roughly 2, depending on what level of confidence you want. So if you want 95%, that goes with a z critical value of 1.96 times the standard error. And so this confidence interval would tell you the range. I'm going to get it right here. I never say it right when I need to because I hate confidence intervals most of the time. That is the range in which the mean would fall in 95% of the samples. I don't think that's quite right, but it's close enough. I hate confidence intervals. This one I like though. This one's easier. So what goes into the second part here is the square root of the random intercept variance, the variance of these U0s. So here's a intro stat review. Can you give me the name for what the square root of a variance is? Yeah. But put yourself back. What's the square root of a variance? Standard deviation. Yes, it is. And so when you were first learning about the normal distribution and people talked about things being within about 2 standard deviations as where 95% of the distribution would fall, that's the same idea here. So what this means basically is the middle is the average cluster mean times 2 standard deviations around it. So this interval goes from 32 to 49. What it's telling me is for my sample, this is the range in which I would expect 95% of the individual school means to fall. So now I can talk to my school administrator and be like, look, across all the schools, 95% of them have a mean between 32 and 49 on this scale, where on average it's 41. So this can help to convey on the scale of the outcome how variable your clusters are. If the range across schools had an average of 41, but it ranged from 40 to 42, I'd be like, who cares, right? That's a very small range of mean differences. That would translate into a very small intraclass correlation. But this, 32 to 49, is quite large. So this is as a sort of a layperson kind of way to describe the extent of the variability across clusters using the metric of the outcome. So something else that can be useful in just describing what your models mean. Okay. All right, how are we doing? So I've been operating under the assumption so far that we need this multi-level model. What if reviewer 2 wants you to do a significance test? Could we do that? The answer is almost always yes. But I have this thing right here. I haven't explained this thing yet. But in general, this sign means no, or stop it. What it is over is where the z test statistic and accompanying p-value would be for here. And I'm saying don't look at these because they're based on the idea that each of these variances has a normal sampling distribution as to what it could be. Now, however, what's the smallest number that a variance can be? What's the lowest amount of variance you can have? Yeah, none, right? We call that a constant rather than a variable if you have a variance of 0. So if you're thinking about testing whether a variance is different than 0, and the variance in question is close to 0, if you picture like what a sampling distribution would be for that, it can't be two-sided and symmetric because you're going to hit a wall where 0 is, right? Like it's going to get stuck. So these p-values here are predicated on the idea that each of these variances has a normal sampling distribution that's symmetric and two-sided. And for large samples and for large variances that get far off of 0, that might be true, but the closer you get to 0, the less that is going to be accurate. So we don't want to use these p-values, even though they can show up on some of your output. I don't know that Stata provides this by default, and I know that R does not, and these are the reasons why. In SAS, you have to ask for it, but we don't want to use those. Instead, what we want to do is a different type of test that most of you have seen before, but not necessarily. So in terms of answering the question, how do we evaluate whether we've added something to the model and it helps? If we're talking about a fixed effect, then that's easy. If I add a new predictor to my model, the null hypothesis is 0, the sampling distribution is normal, symmetric, two-sided, I can stare at the p-value that shows up on that estimate divided by standard error all day long, no problem. For the model for the variance, though, the idea of do we need that random intercept? Do we need a two-level model? We can't just stare at the p-values. Instead, we have to look at an index of model fit based on the log likelihood of the model. So we are going to be doing what is known as a likelihood ratio test. So very briefly, what we're going to be using as the core ingredient is something called log likelihood. The idea is, given the best estimate of the model parameters, we use the multivariate normal distribution to figure out how tall each cluster's set of outcomes is. Under the assumption that clusters are independent, which is what we would say in a two-level model, we take the likelihood that the formula's result, take the log of it, and we add all them together, and the sum of that is something called log likelihood. Log likelihood is an index of model goodness, where taller is better. We want the data to be taller, and we add things to the model to try to make the data taller. This statistic comes in two different flavors, I will say. There's regular flavor maximum likelihood, or residual or restricted maximum likelihood, otherwise known as REML. And to make this even more complicated, what you get for this depends on what software program you're using. So sometimes you will get this value of height, in which more is better, multiplied by -2. So that flips the direction around so that smaller is better, and it's actually lack of height or shortness. So if you use SAS mixed, SPSS mixed, and certain R packages, this is what you get. If you use Stata anything or M plus anything in certain R packages, you get log likelihood. So either way, we're going to use this value to figure out how much better our model is by adding a random intercept relative to a single level model that does not have a random intercept. The reason why some software packages take this log likelihood and multiply it by -2 is because they knew that's what you would need to do to compare. So -2 log likelihood from the model that has fewer parameters minus the -2 log likelihood from the model that has more gives you a value that is treated as a chi-square. If you given log likelihood, the idea is the same. You can subtract them and then multiply by -2, and that gives you an equivalent result. So either way, you get to the same place. You then compute the degrees of freedom for the comparison, which is the number of things you've added. So in this context, for instance, if I go from a model that has one fixed intercept and one level 1 residual variance to a model that adds a level 2 random intercept variance, I've added one thing. Thing meaning parameter. That means that I would go to a chi-square distribution with degrees of freedom 1 for the number of things I've added to figure out how likely it is that I got a result that big based on the shape of the distribution. So where 0.05 is for the cutoff of not likely for our alpha level is 3.84. So I would take the result of this difference in -2 log likelihood, and if it's greater than 3.84, I would say yes, it helped the model p less than 0.05, the end. So this process of likelihood ratio test shows up everywhere. It shows up in generalized models. It shows up in factor analysis. It shows up in structural equation models. It shows up in mixture models. Anything I'm forgetting? Like everywhere. Like everywhere in statistics, you will do this. Sometimes it's called a chi-square test. Sometimes it's called a deviance test. I try to stick with the term likelihood ratio. What its likelihood, it would be actually division of fewer divided by more. Once you take the log, division turns into subtraction. So the term is a little bit off from how it's operationalized, but it's a log likelihood difference or a likelihood ratio. So then that's how we would do any kind of model comparison involving the model for the variance, any random anything ever. Take the log likelihood from the model without it versus the log likelihood from the model with it, and see if what you added helps enough, where enough is your chi-square distribution as a reference. Okay, does that make sense? That much? Yes. And you get to do this in software. So in a lot of my examples, including example 2, I have an Excel sheet because there's a function in Excel that will do this for you. It's chi-dist is the old function. There's modern versions that basically do the same thing. That will give you a p-value that corresponds to a chi-square test statistic in degrees of freedom. Stata has a routine called LR test. R has something called ANOVA, which is the worst name for this ever because it has nothing to do with ANOVA. And in certain packages, it's RANOVA instead of ANOVA. But point being, this is built into software. You don't have to compute anything by hand unless you choose to or are using a package where that's not something that's built in. One caveat before we call it a day. Whenever you're adding a variance that can't be negative, the chi-square distribution that you should compare this result to is actually technically supposed to be a mixture. Because the situations in which it would have gone below 0 can't happen. So to be more correct, you would want to refer to a mixture of degrees of freedom 0 for when the variance would have gone negative and couldn't, and degrees of freedom 1 for when the variance is positive like it's supposed to be. A chi-square with degrees of freedom 0 is 0. So what that amounts to is you can just cut your p-value in half. So in practice, when you add a random intercept, the critical value is 2.7 rather than 3.8. So very few situations in which you would need to care about this, but just to be thorough, I have an article on your reading list that gives you more technical details. For this situation, it's pretty straightforward. The more complex your model, the less straightforward it gets. But you will see people talk about this as a mixture of two different things. All right. So basically, if you add parameters to your model can get worse or better or not better. If you take parameters away, it gets worse or not worse. And that's the way I would talk about it. Other things that people look at are called information criteria. These are adding on to -2 log likelihood as their basis. So these are indices of shortness, where smaller is better. AIC adds a penalty of 2 times the number of parameters, whereas BIC adds the log of sample size times the number of parameters. And yes, there is debate about what n should be. In some packages, it's level 2 units. In some packages, it's all the units. Here's an example using SAS. So this is output that gives you log likelihood times -2, as well as a few information criteria. So this is the model that does not have a random intercept. This is from the model that does. So I take the model without fewer minus more, and there's my test statistic. So the difference in -2 log likelihood is my chi-square test statistic. I would compare that to a distribution where the critical value is 3.84 if I'm doing it the lazy way, or 2.7 if I do it the proper way. Either way though, yeah, wildly significant. So that means in context that this interclass correlation of 0.22 that conveys the effect size for how large the random intercept variance is across level 2 clusters is significantly greater than 0. So that's what I would tell a reviewer too. Yes, I need a multi-level model because my interclass correlation is significantly greater than 0. I know that because the model log likelihood got significantly taller or less shorter after I added my random intercept variance. And because it's just the variance, it doesn't matter how many clusters I have. It's still one parameter from that perspective. There. That's enough for now. How are we doing? You're like, I'm doing well because it's done now. I know. Sitting on Zoom is not the most fun, but I bet it's more fun than COVID. Can we agree on that? You could be sitting on Zoom with COVID, then everything is the worst. All right. Any questions before we call it a day? No? All right. I'll hang out for a few minutes in case anyone wants to talk to me like usual. Otherwise, thanks for being here. I'll let you know about Thursday. I'm going to retest tomorrow and we'll see. We'll see. Have a good one, folks. See you on the other side.
Lisa, can I